So we looked at absolute extrema, which is the general word for minima and minima, or minima and maxima, I mean. And of course, with there being an absolute minima and maxima, this implies that there's some other type, right? So let's just consider a function such as this one. Okay, and let's say we cut it off here. And let's just say this is at like 4 and this is at maybe -5. And again, the actual values don't really matter too much, but just so we give them names. So we can see here that the absolute max is at x equals 4, and the absolute min is at x equals -5. Okay. But what about these 2 points? Like, namely this point and this point. They feel like they warrant some kind of mention still, right? Because this isn't the largest point, but if we were to condense our interval a little bit, right? Like if we were to cut off the interval, say at here and here, then it would be our largest point, right? So it's the largest in a sense, right? It's the largest of the points that are around it. And same idea with this one down here. It's the smallest point in that area. So we would say that that this point right here is the smallest point locally, and that this point is the largest point locally. So we call these local maxes and local mins. So this would be a local max, and this would be a local min. Okay, so let's write out the definitions for these. So we say that a function f has a local maximum at C if there exists an open interval I containing C such that I is contained in the domain of F and f of C is greater than or equal to f of x for all x in I. Okay. And then you can just flip this around for a local minimum, right? F of C is less than or equal to f of x. So we need to be able to, at the point C, where we suspect that there's a local maximum or minimum, we need to be able to make an open interval I around that point, which is still in the domain of F, right? We don't want to exit the domain of F. And it needs to be, in the maximum case, larger than all of the points, the other points in that interval. Okay. So with something like this, right, we can clearly do that. Or if we want a more concrete example, let's just take a look at x squared again. Okay. Now, something being an absolute minimum doesn't preclude it from being a local minimum, right? The definitions are kind of independent. Something can be a local minimum, but not an absolute minimum, right? Or it could be a local minimum and the absolute minimum. So if we look at this point 0, 0, right, we can make an interval, an open interval around that point, like say just from -1 to 1. And -1 to 1 is in the domain of x squared, which we'd say is negative infinity to infinity. This is supposed to be like a sideways U, which is how we say that sets are contained in other sets. So let's just make sure we have all the conditions here. So we're looking at C equals 0. So there's an open interval I containing C, right? 0 is definitely in negative 1 to 1. It's contained in the domain of f, and then we need f of c, in this case, less than or equal to f of x. So f of 0, which equals 0, is less than or equal to f of x for all x in negative 1 to 1, right? This is a symbol that means for all, and upside down A. Upside down capital A. So this fits our definition for a local minimum. Okay, so this is a local minimum. So you don't necessarily need to go ahead and construct these intervals every single time. I think, graphically, it's usually pretty clear whether something's a local minimum or maximum, and we'll have a better system for this using derivatives anyway. So here I just wanted to introduce the concept of a local minimum and how it's different from an absolute maximum or minimum. So naturally, you can imagine a lot of situations where we're interested in finding the absolute maximum or minimum, finding the largest point in a set or the smallest point in a set. It could have a lot of applications just in terms of like optimization, which we'll look at examples of later on. But generally, the process would be to find all of the local extrema and then look at the endpoints, assuming you have endpoints, if you're on a closed bounded set. And then those are basically your candidates for your absolute max or mins, right? Those are all of the places where you could have a largest or smallest point. So if we return to one of the examples we looked at, this one right here, if we're trying to find the absolute max, what we would do is we would find the local max and we would check the endpoint. So we'd see that this is a local max, and then that would be a candidate for the absolute max, and the endpoints would also always be candidates for the absolute max. And we would just look at what all the y values are, and whichever one has the largest y value would be the absolute max. So in that case, it would be this one.